Mounting is not only about attaching storage so it becomes visible. It is also about choosing the rules under which that storage participates in the system, and those rules can meaningfully change both security risk and day-to-day stability. The exam likes mount options because they are a clean example of Linux being a system of deliberate trade-offs, where a choice that increases convenience can increase exposure, and a choice that tightens safety can sometimes reduce functionality. New learners often treat mounts as either working or not working, but mount options live in the middle space where a file system can be mounted successfully and still be mounted in a way that is risky, inefficient, or surprising. This episode is about giving you a practical sense of which mount behaviors commonly matter, what kinds of scenarios make a particular behavior desirable, and how to reason about the consequences without needing to type anything. By the end, you should be able to look at a mounting scenario and think about safety boundaries, stability expectations, and least privilege, because that is the mindset the exam is testing. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A useful way to start is to connect mount options to the idea of a trust boundary, because mounting is where you decide how much you trust the content on a file system. If the file system holds the operating system itself, you usually trust it and you need it to behave in a way that supports normal program execution. If the file system holds removable media from unknown sources, you should be more cautious because you do not control what might be on it. If the file system is used only for data storage, you might not need to allow code execution from it, which means you can reduce risk without breaking normal usage. Mount options are the mechanism that lets you express these differences in trust and intent, making the system more defensible. The exam often describes these situations indirectly, like a system that mounts removable storage or a file system meant only for uploads, and then asks for the safest choice. Your job is to connect the scenario to the trust boundary and choose the behavior that limits the damage if the content is malicious or if a user makes a mistake. This is not about paranoia. It is about reducing unnecessary capability, which is a core security principle. One common security-relevant behavior is whether programs stored on a file system are allowed to be executed directly. Execution matters because allowing a file system to execute code means an attacker who can write to that file system might be able to place a program there and run it, potentially bypassing other controls that assume programs come from trusted locations. In many systems, certain locations are meant for executables, like system directories, while other locations are meant for data, like uploads or external storage. If a file system is purely data-oriented, it is often safer to mount it in a way that does not allow direct execution, because that reduces the likelihood that malicious content becomes runnable just by being present. The exam likes this concept because it is a straightforward application of least privilege. Do not allow a capability you do not need. This does not mean execution control is the only security measure, but it is an important layer because it limits one common pathway attackers use, which is planting and running code from writable locations. When you see an exam scenario about user-writable areas or external media, think about whether execution should be restricted. Another security-relevant behavior involves device files, which are special entries that can represent hardware or pseudo-devices and can be used to interact with the system in powerful ways. If a file system is treated as a place where device files can be created and honored, that can open strange attack surfaces because device file semantics interact with privileged parts of the system. For many data-oriented file systems, there is no good reason for device files to be meaningful because the file system is meant to hold ordinary files, not to define new interfaces to the kernel. Therefore, security-minded mounting often includes restricting the honoring of device file semantics in places where they are not needed. The exam may not phrase it as device file semantics, but it can present a scenario where removable media or user-controlled storage should not be able to introduce special files that the system treats as devices. When you frame it as reducing unnecessary kernel-facing capability, the reasoning becomes simple. If the file system is not part of core system operation, treat it as untrusted and limit special behaviors. This reduces the chance that an attacker can use the file system to influence the system in unexpected ways. The larger point is that mount options are a frontline way to prevent untrusted storage from behaving as if it were system storage. A closely related security behavior is whether the file system allows programs to run with elevated identity features that can change how privileges behave when an executable is run. Linux has mechanisms that allow a program file to run with different effective identity under specific conditions, and those mechanisms can be useful for certain system tools, but risky in user-controlled locations. In a system directory where software is controlled and managed, those features can be part of normal operation. In a user-writable file system, those features can create privilege escalation opportunities if an attacker can place or modify an executable. Therefore, a common security posture is to restrict those elevated identity behaviors on file systems that are not part of the trusted system code base. The exam often tests this in the form of a best practice question, where the correct answer limits privilege-related behaviors on an untrusted mount. The core reasoning is again least privilege. Do not allow privilege-boosting behaviors in areas where untrusted users can write. When you connect this to your earlier understanding of FHS, it becomes even easier because you can treat system directories as trusted code zones and data directories as zones where you should limit privilege-related execution behaviors. Mounting becomes a way to enforce that zone separation. Now let's pivot to stability, because mount options are not only about security. They also influence how reliably a file system behaves when the system is under stress or when failures occur. One of the most important stability-related ideas is how the system handles errors on a file system, because errors can happen due to hardware problems, corruption, or unexpected conditions, and the system needs a policy for what to do next. In some cases, continuing to write to a file system when errors are detected can make problems worse, while in other cases, stopping immediately can create downtime that may not be necessary. Mount behaviors can influence whether a file system becomes read-only when errors are detected, which can preserve evidence and prevent further damage at the cost of functionality. The exam may describe a scenario where a file system suddenly becomes read-only, and your job is to recognize that this can be a protective response rather than a random bug. Understanding that file systems and mounting policies can switch into protective modes helps you interpret symptoms calmly. Stability thinking also includes recognizing that a system that stops writing because it is protecting itself is often signaling a deeper underlying storage issue that needs attention. Mount options help define how cautious the system is when things go wrong. Performance and stability also tie into when the system chooses to write data and metadata to disk, because different choices can reduce the chance of data loss at the cost of performance or improve performance at the cost of a higher risk window. Many file systems use buffering and delayed writes because writing every change immediately can be slow, but buffering means there can be a gap between what an application believes is written and what is actually on stable storage. Mount behaviors can influence this trade-off, and the exam may test whether you understand that faster does not always mean safer. In environments where data integrity is crucial, you might prefer behaviors that reduce the chance of losing recently written data during a crash. In environments where performance is more important and the data is less critical or can be regenerated, you might accept a larger risk window. The exam does not require you to tune systems like an expert, but it does require you to recognize that such trade-offs exist and that the safest choice depends on the scenario's requirements. When a prompt emphasizes critical transactional data, you should lean toward integrity-preserving choices, while a prompt emphasizing scratch data might allow more performance-oriented choices. Stability is about aligning behavior with the consequences of failure. Another stability concept that mount options touch is the difference between automatic behavior at boot and on-demand behavior later, because a system might behave very differently depending on when and how a file system is mounted. Some file systems are essential and must be mounted during boot, while others can be mounted only when needed, reducing boot dependencies and avoiding failures that stop the system from reaching a usable state. This is a stability trade-off because mounting everything early can make the system more immediately complete, but it also increases the risk that a single unavailable file system causes a boot failure. Mount configuration can express whether a mount is required or optional at boot, shaping how the system reacts when a file system is missing. The exam often frames this as avoiding boot time surprises, such as making sure a missing external drive does not prevent the system from starting. This connects directly to the earlier lesson on FSTAB as a boot contract, because the contract can be written in a way that is strict or in a way that is tolerant. The safest answer depends on whether the file system is truly required for the system's purpose. A good student can recognize that optional data should not block boot, while core system file systems often must. Network-based file systems introduce another layer of stability trade-offs because they depend on network availability and server readiness, which are not guaranteed at the earliest stages of boot. If a system tries to mount a network file system before the network is fully available, it can delay boot or fail, which can cascade into other problems. Mount behaviors can control whether the system waits indefinitely, waits for a limited time, or continues booting while leaving the network mount unavailable until later. The exam may describe a system that hangs at boot due to a mount attempt, and the correct reasoning can involve recognizing that a mount that depends on the network should not be treated the same way as a local disk mount. Even without naming specific options, you can understand the stability principle. Reduce early boot dependencies on services that might not yet be ready, and favor on-demand mounting or tolerant mounting where appropriate. This principle matches the exam's focus on minimizing risk and avoiding avoidable outages. It also ties back to the boot flow story, because boot is a staged process and the network is not always ready when storage mounting begins. Mounting mastery includes anticipating that timing. Security and stability trade-offs often collide in the realm of removable media and user-controlled storage, because these are common pathways for both performance surprises and attack risk. Removable storage may be slow, may have unusual file system structures, or may contain malformed metadata, and mounting it with overly permissive behaviors can expose the system to both security risk and instability. A cautious mount posture can limit what the system will do with such storage, which can prevent certain classes of exploitation and reduce the chance that the system treats untrusted content as a privileged interface. At the same time, too much restriction can break legitimate workflows, such as needing to read specific file types or transfer data. The exam will usually guide you by the scenario's intent, like whether the media is trusted or not, whether it is meant to be executable or not, and whether the user needs broad capability or just basic access. The correct answer is rarely to allow everything everywhere, because that violates least privilege, and it is rarely to lock everything down without context, because that ignores usability. Instead, the exam rewards context-aware trade-offs where you allow only what is needed for the described use case. When you reason about the intent of the mount, you naturally find the right balance. A practical way to unify all of this is to treat mount options as policy statements, and policy statements should match the role of the file system. System file systems that host core binaries and libraries need behaviors that support normal execution and privileged tools, but they are also tightly controlled and not broadly writable by untrusted users. User home file systems need usability and persistence, but they also benefit from certain restrictions that reduce the chance that user-controlled space becomes an easy execution or privilege escalation path. Temporary file systems, especially those that are memory-backed, need behaviors that support speed and appropriate cleanup, but they must be constrained so they do not become a pathway for abuse or a source of unpredictable resource exhaustion. Removable and external file systems need cautious handling because they can bring untrusted content and unusual metadata into the system. Network mounts need stability-aware behavior because their availability is not guaranteed at boot and their performance depends on the network. The exam may not label these roles explicitly, but the stories usually contain enough clues to identify what role the file system plays. Once you identify the role, the correct mount policy becomes easier to infer, even if you do not know the exact option names. Another key idea is that mount policy is part of defense in depth, meaning it is not your only protection, but it is a valuable layer that reduces the impact of failures and attacks. If an attacker can write to a file system, restricting execution and privilege-related behaviors can prevent a simple write from turning into code execution with elevated impact. If a file system experiences errors, having protective behavior can prevent further damage and preserve system integrity long enough to investigate. If a network mount is unreliable, tolerant boot behavior can prevent a single external dependency from taking down the whole system. These are not perfect guarantees, but they are meaningful risk reductions. The exam often rewards layered thinking because it reflects real system design. You do not rely on one control to save you. You use multiple small controls to reduce risk at multiple stages. Mount options are one of those small controls that can have outsized impact because they apply every time the file system is accessed. When you remember that, you treat mounting decisions as part of security posture rather than as an afterthought. By the end of this episode, you should be able to explain that mount options matter because they define the rules of behavior for a file system, and those rules shape both security exposure and stability under stress. You should be comfortable reasoning about trust boundaries, recognizing that untrusted or user-controlled storage should generally have fewer capabilities enabled, especially around code execution, device-related behavior, and privilege-affecting behaviors. You should also understand that stability trade-offs exist around error handling, write behavior, and boot time dependencies, and that the right choice depends on what the system must prioritize in the scenario. Most importantly, you should be able to read an exam prompt and ask two grounded questions that lead you to the right answer. What is this file system's role and trust level, and what failure would be most damaging if this mount behaves incorrectly? When you answer those questions, you naturally select policies that align with least privilege and operational reliability. This mindset prepares you for the next topic on network mounts, because remote storage pushes these trade-offs into sharper focus and requires even clearer thinking about timing, trust, and what symptoms look like when the mount is not behaving as intended.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.